And welcome, Mindsetters, to this session of Learn Extra Live for you guys just on the Sunday so you can get your questions in so you can be nice and prepared for your exams. This is exam school, so Mindsetters, I hope you guys have your pens and pads out and you're going to make some notes. I'm Ty and I'm here with Phil, who's going to be taking us to today's session. Phil, how are you doing?
I'm great, thanks, and you, Ty?
Good. What are you doing today?
Well, I'm going to be taking a look at some of the past papers. I'm going to be answering some of your questions on the page. We're going to be doing everything we can help you with those last few questions. I'm going to be taking a look at some equilibrium first.
All right, awesome. So
Cool.
while you make your way across to there, Mindsetters, do not forget, keep using the page, chat to me, let me know what you guys are thinking. I know for a fact that you guys are writing tomorrow, so this is probably the best chance you're going to have to get all your burning questions in so you can make sure that you can get those papers done and pass them and do well, you know, and then have your parents going, ooh, my child, ooh. But yes, make sure you get on the page. Talk to us. Let us know. And don't forget, also sign up on Curio. That's going to help you guys a lot more. And you can also email Mindset at helpdesk@learnextra.co.za. So make sure you just use them. They're utilities for you to help you pass. Because we want to pass, we want to raise the pass mark for the year, so make sure you get on the page and chat to us. But for now, we have a session to do, so Phil, take it away.
Thanks so much, Ty. Okay, well, as I said, the first section which I'm going to be taking a look at has been taken from the 2008 final paper, so that's November 2008. If you guys are looking for past papers, they're all over the web. They're on our webpage. Get on there and get the papers. Now, I've been taking a look, and a lot of you guys are just watching the program. That's not the way to do chemistry. Guys, you've actually got to be taking notes. You've actually got to be putting pen to paper. It's not going to work without it. Okay, and this is a great example. I'm going to be doing this in 2 segments, and it's a classic question because it's always asked, guys. Okay, KC, equilibrium graphs. These are guaranteed questions. So make sure that you take some notes as we go through this. I'm going to be dropping a few hints as we go along, so write those down. Okay, so now we've got our equilibrium question. It says the following equation represents a reversible reaction that has reached equilibrium at 470 degrees there. Okay, so I'm just going to highlight the important information because temperature is important to equilibrium. And it tells us that this is in a closed container. Okay. So our reaction is put over there. So I've got N2 plus H2, so my reactants over there. So there we go. Let's tick them off as we go. So my reactants over there, both gases, are reacting to give us ammonia. Now, for those of you studying chemical systems, you should be doing this section first because this is actually one of those processes which you need to know. This is the main process used inside the Haber process. Sometimes it's called the Haber-Bosch process. Okay, but this is the Haber process, and this is used to make ammonia. Okay, so now we're going to do some changes to that equilibrium. We're going to see how they're influencing, and we're going to follow the concentrations and the amounts of these chemicals as time goes by. Okay, so it says a change was then made to the NH3. Okay, now that's quite important. A change was then made to the NH3. Okay, now this is a little bit strange. Grade 12s, it's really, really weird to make a change to only one thing inside a system. Now, it's usually something which I can change. I can change about the whole system, the pressure, or I can change the temperature. Now, it's quite unusual that I affect only one of those reactants or products. Okay, so that's the first clue that something strange is going on. In the equilibrium mixture at T2. So at at time 2, let's take a look on our graph there. Okay, so at time 2, let's look for time 2. So they're telling me something happened at time 2 on my graph over here. Something was changed about my NH3. Now what I'm going to do is just highlight that graph, and let's actually follow the NH3. Here we go. So NH3 over there is now green. Okay, NH3 at time 2 did something very strange. It jumped up before finding a new equilibrium. We're going to discuss this graph now in great detail. Let's just make sure that we're highlighting the correct one. Okay, guys, please, these questions are going up on the page. I want you to work with us. Okay, now we're going to take a look and see what that change to NH3 was. Now, the first question is very, very obvious. And it starts to take a look at what is the meaning of the horizontal lines between T1 and T2. Okay, so let's look at those horizontal lines. Now, these horizontal lines are there for a reason. Okay, horizontal lines, what does it mean? They are flat. And why are they flat? Let's just start to take a look at why these lines are going flat. Now, grade 12s, please, in the way that you explain this, you cannot say, okay, it's equilibrium because they're flat. That won't get you your marks. They're telling you that these lines are flat. They're not going to give you marks for telling them what they already know. You need to explain why the graph is flat. We need to explain the significance. So I need to say, okay, the graph is flat. Then what? So let's take a look at those graph lines and let's see why they're flat. So there we go. Let's take a look at these flat regions. Okay, between T1 and T2, I see some flat lines over there. I see flat lines over there. I see flat lines over there. Wait a minute, something interesting is going on here. I can see, and this is the correct way to say it, as time passes, here we go, as time passes, the amount of gas is staying the same. Grade 12s, that's very important that you explain it in the correct way. What does it mean to have a flat graph? Does it mean that I just pulled out a ruler and made a flat line? Well, yes, it does, but what is the significance of that? I need to say, okay, the amount of gas is remaining the same of all of them. So the reactants remain the same, the products remain the same. Now there's a second mark as well. So let's make our conclusions here. Okay, why do I have a flat graph? Well, there's two things which I expect you to say, and this is very important, because Tracy's been telling me you guys haven't been explaining properly, and she's right, because I've been on some of these marking sessions, and you guys say, okay, well, the line is flat, therefore I know this. But you've made your conclusion from the way that they've said this. So here's the two things I want you to say. I know that the concentration, now I'm going to abbreviate a little bit just to make sure that we can fit it in here. So the concentration of my reactants and products. So my reactants and products is staying the same. So that's quite important. Why is that the important thing? So the concentration of the products and the reactants stays constant. Now I can make a conclusion from that. Now I can say that I've got equilibrium. I can make a conclusion from this. So I can say, therefore, equilibrium. I know that when the amount of reactants and products does not change over time, that equilibrium is reached. There we go. So those are the conclusions. Okay? Now, it depends on how many marks they want to give out for this, but please, they can actually ask you further on. Why is it horizontal? Well, yes, there is equilibrium, but why? I want you guys to remember this. Okay, so now we've got to state the change. Now, this is the tricky part. I've got to be able to read graphs. It says, state the change that was made to the NH3. Now I'm watching the NH3, the one which I colored in green, in the mixture at time T2. Okay, so that's quite important. Only one mark, that means that it's usually just an observation. So on my graph over here, let's take a look. All right, so at T2, let's follow. Let's just make a bit of space over here because this is getting a little bit cluttered. Let's just make sure that we've got a little bit of space and make sure that we've got a clean graph. Okay, so at T2, let's actually make a line here and let's point out the significance at T2. There we go. So at T2, something interesting is happening here. I see that NH3 starts out at a certain concentration and ends up at a much higher one. Now that tells me that NH3 suddenly went up. Guys, this is a dead giveaway. This means that something was added to the system. If you can see the concentration of one of your reactants or your product suddenly jumps up, the only way that you can make such a sudden change to your equilibrium is by injecting something or changing the concentration suddenly. So what happened? My NH3 went from being a low amount to being a very high amount, very, very short space of time. So I can see that increase of NH3 at T2 over there. Okay, so that's very nice. It's a very nice clean answer there. So we're going to say what the change was. All that happened was the amount of NH3. So I injected or added. So we added more of my NH3. So what that did was we were adding lots of product into my equilibrium. Okay, so now we're going to start to take a look at the actual equilibrium stuff. We're just observing off a graph at the moment. Now it's asking us to explain. Now this is getting into the upper levels of thought, and I've actually got to figure out what is going on here. It says to explain how the change mentioned in question 9.3. Okay, so the change which was mentioned in 9.3, so they're asking us to say, how did the amount of NH3, so I added a whole bunch more NH3. there's more NH3 inside there. Now, how is that going to affect the concentration of H2 and N2 gases as shown in the graph? Okay, now, what we've got to say, and this is now for 3 marks. So it says, explain how the change mentioned in question 9.3 affected the concentration of H2 and N2. So there's a couple of questions here which need to be answered. First of all, let's figure out where things began. Guys, the way that you explain things is where you're going to get your marks. 3 marks is a very big deal in your final exam. Several percent in there. That might be the difference between symbols. Okay, so explain how the change mentioned. So how did the increase in NH3 affect the concentration of H2 and N2? Okay, well, first of all, let's just point out what we have done. We have made more product. And teachers really generally don't mind if you answer in bullet form, especially in science, because you're making your points as you go through and you're answering in brief sentences. They've got to be complete sentences, but they don't want entire paragraphs that go nowhere. They prefer bullet form. If you're trying to get your thoughts organized, it's a nice way to start. Okay, so now I've got more products. Okay, now what I've got to say is that the reverse reaction, why? Okay, so the reverse reaction is favored. Why is the reverse reaction favored? Well, remember that guy Le Chatelier? Le Chatelier says that if I make a change to a system in equilibrium, the system will favor a course of events or favor a reaction which will oppose or remove the stress. Now, what is the stress? My stress is more product. What does the system want to do? Well, the system wants to decrease the amount of product because we added more, the system wants to get rid of it. The only way that the system can do this is by the reverse reaction being favored. So the reverse reaction is favored. Okay, now we've got to make a conclusion after this. Notice how this goes in a logical thought pattern. The way that I structure this is very, very important. So I've got more product, so the reverse reaction is favored. If you want to give a reason there we go, Le Chatelier. Okay, now you may not feel comfortable spelling it, and I sometimes get it wrong, but that's okay. Right, so Le Chatelier, this is the guy that explains it, and this is the principle which is being applied, and then I've got to make my conclusion. So what's happening? H2 and N2 will increase. Okay, so I can find that the amounts of N2 and H2 will therefore increase. There we go. So what we're going to find is exactly what we see on the graph. So let's just go back and see if we're correct on our graph over here. So I looked to see very, very carefully. I injected the NH3. There it is. There's my change. So what happens as time goes by? What I notice is that my reverse reaction is being favored by this. So my H2 is going to follow a higher path, and my N2 is going to follow a higher path. For those of you that are really taking a look at some of the ratios inside this graph, it's actually quite interesting to see that the H2 over here, so the H2, let's just actually make a nice dotted line there for you. So as time goes by, and as time goes by for my N2 over there, what I can see is that there's actually a ratio here. So this is just for those people going, why does the H2 increase so much more? Because remember, my reaction goes to 3H2, and this is just N2. That's the reason that the H2 is increasing so much more than the N2, because of that increase in NH3. Okay, guys, you have to be able to read these graphs very carefully. Now, as I've said for physics, and physics is now done, I want you to start your sentences with a y-axis. So if I was trying to describe the way that something was happening on my graph, the first words in my sentence should include my y-axis. The amount of gas H2, something, 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 so remains the same. So I can actually follow this from left to right on my graph. So I start my sentence here. I say the amount of gas of H2 increases as time goes by after T2. Notice how I've got to structure my sentences very carefully, because that's actually one of the biggest ways to lose marks in your explanations inside chemistry. Really nice and complex question, but I think, Ty, what I'm going to do is I'm going to break it up into smaller pieces. I think this was a lot to digest. What do you think?
I think so too. I think we need to give them a little bit of a break so they can kind of digest it all piece by piece, then make sense of it.
Absolutely, let's do that.
All right, so mindsetters, I'm loving what you guys are doing on the page. Keep on posting. Let us know what you guys are thinking. If there's any particular sections you'd like us to cover, let us know. Don't forget the help desk email address. But yes, we'll see you after this break. And welcome back, Mindsetters. Hope you had a nice little break, because we're back like a spine. Anyway, moving right along. Yes, we actually just did a quick little magic trick right now. So Phil has kind of stepped out, and then now we have Tracy in. So make sure you keep getting those questions in on the page. You know the link, www.facebook.com/learnextra. Yes, I'm just putting it out there so you know what to do. But yes, on that note, keep on sending us your questions, and I'm going to hand it over. Tracy, take it away.
Thanks, Ty. And guys, with the back and the spine thing, just smile and nod. It's just easier.
Yeah, just.
Okay, well, yeah. Anyway, guys, to start off with, I just want to quickly remind you about the whole Curio page on Mixit. Okay, so remember, when you go to do an assignment, you need to enter on the home page, go to click enter Curio, and then the codes. Okay, so remember, today's the codes for which are going to help you for tomorrow's exam are PCI-25, which is grade 11 chemistry, PCI-26, which is rates and equilibrium, PCI-27, organic molecules and reactions, okay, and of course PCI-28, which is electrochemistry. Start the assignments, get them going, select the most correct answer, and then of course click submit afterwards. Now we do have a competition that's going, okay, we can't reveal anything about the prizes. I can tell you though that it's better than just a calculator. Yay, very exciting, but in order to win on this, it's about getting the most submitted assignments in. Okay, so you've got to actually do the assignments. You can't just open them, you've actually got to do them and submit them. Okay, now in order to get more details about the competition, stay watching, because tomorrow afternoon from 3:30 to 5, there's going to be the live show for maths, because of course after chemistry the next big one is maths for a lot of you. I think English or something's in the middle, but hey, that's another subject. Maths is on Friday, so keep watching. We're going to do a live show tomorrow, 3:30 to 5, and then they'll give you more details about the competition. I really think this is a great way to do a lot of revision, guys. I know, looking at the stuff you're sending through to us, electrochemistry, rates and equilibrium, all these are actually the sections that you're really struggling with. So this is a really good way to start revising, work through them, guys. Don't try and rush them, do them slowly, work through the problems. Okay, but get onto that Curio page on Mixit. Okay, so what we need to do is I need to find my questions. No, that's Phil's. No, that's not mine either. There's mine. Brilliant. Okay, so we're going to do some organic chemistry, and we're looking at a question from one of the 2009 papers. We've lost track as to which one it was, whether it was the leaked one or not, but it's a great question. So now it says to us that the table below shows the results obtained during a practical investigation. 2 experiments were performed to determine the boiling points. Okay, so we're looking at boiling points. We've got 2 experiments of different compounds from 3 different homogeneous series under the same conditions. Okay, so same conditions important. We're looking at different series, and each letter A to F represents the organic compound written in the block next to it. So now we look at this and we go, all right, what we have over here is, this is a carboxylic acid, this one is an alcohol, and this one would be that's an aldehyde. Okay, but what's important here is we look at this and we go, okay, the molecular mass is relatively the same. Look at the next one. Okay, molecular mass, all 3 have got the same molecular mass, but now we have ones that are branched. Okay, as soon as we put, still we've got an acid, an alcohol, and aldehyde, so we've got 3 different groups. Okay, same molecular mass, so we're trying to keep them about the same size. With D, E, and F, so the second experiment, we're actually branching it more. Okay, so we're actually putting on extra branches, and we're seeing what that does to the boiling point. Okay, first thing, they say to you, name, and we've just done it. without even thinking about it. Said name the series to which each of the following pairs. So the first one is A and D. And if we look at it, see it says COOH at the end. That tells me that it belongs to the carboxylic, and I can't spell today. Carboxylic.
That happens.
Yeah, and that happens all the time. It's Sunday. Okay, guys, please be careful. Please don't just write it belongs to the acids, all right, because we get inorganic and organic acids. It's specifically the carboxylic acid, so it's an organic acid. B and E, they've just got the OH at the end. That means they belong to the alcohols. Okay. And then the next one, I said to you, belongs to the aldehydes. And now you've got to remember this. Remember, the difference between ketones and aldehydes is that your ketones, your oxygen has to sit in the middle of the chain. So we can't, if we're doing it like this and we're drawing it as a molecular formula almost, okay, and I've written the oxygen at the end, that means it's sitting on the last carbon. If it sits on the last carbon, that makes it an aldehyde, okay, not a ketone. So that's very, very important. Aldehydes and ketones do have different properties, okay? Probably your most well-known ketone is propanone, which is acetone, nail varnish remover, ladies. Aldehyde, probably the best known one is formaldehyde. Those of you who do life sciences, I hope you know what formaldehyde is. It's the stuff we use to preserve organic specimens. Okay, it smells absolutely hideous, but they use it to preserve organic specimens. It's also the reason why I don't like going into our life sciences labs, because they got things in there.
That smell.
That smell, and then they have things in bottles, and no, don't do it. Moving on. So, now we know these. No. Ooh, look here. Write down the IUPAC name for C. Okay, now we look at me and go, let's draw it out. It's going to make it easier, okay? So C is CH3. I'm not going to draw the hydrogens in. I'm just going to make it easier for myself. CH2, CH, and then oxygen, so it's there, okay? We know it's an aldehyde, which means it must end in propanol, not OE. I'm busy calling it a propanol. Make sure your A looks like an A, okay? 3 carbons in the longest chain, so it's propanol, okay, with an A. Next one's a little more difficult, so let's draw that one out, okay? So we have, in fact, it's not a branch chain. I was lying to you. It's actually just, I know, they're not branch. There's just lots of them. CH2s, no, shh, rubbish. Not branch chains, sorry. Those are just much longer chains. So now I've gone over it. Now I can't actually see what it says. Okay, CH3, CH2, and there's 3 of them. So it's going to get quite long. Okay, so we've got CH3, and a nice line going out of nowhere. Okay, CH3, then it said 3 CH2s, 1, 2, 3, and then we had the last carbon and the double bond oxygen. So we go, okay, let's have a look at this. We know it's an aldehyde, we've already decided that. Okay, and I'm doing compound F right now. Okay, guys. This is what not to do in your exam, okay? I'm doing the wrong one.
Perfect example.
This is what happens. So take your time. It's because I'm a little rushed for time, okay? Because I'm going to run out of time. So take your time. Let's just get rid of... Ooh, that's going to take forever. It's too small. Okay, let's do E, shall we? E is the alcohol. I knew there was something wrong. Okay, it was almost right. So we've got CH3. We've got 3 carbons like this. And then we have CH2OH, so it's this. Okay, OH means it ends in an OL. 1, 2, 3, 4, 5 carbons. 5 is meth, eth, prop, but, and pent. Okay, so this is now watch it, pentanol. Okay, make sure the O looks like an O. Let's do the next one. Next question. Formulate the investigative question for this practical investigation. Guys, we are looking for trends in boiling points. Okay, there's 2 investigative questions actually. The first one is how does the functional group affect the boiling point if the mass is kept constant? That's essentially what we're looking at, okay? How does the functional group of an organic compound affect the boiling point if the mass is kept constant? Because that's actually what we did for each of these. We changed the functional group, and then we looked at what happened. We did one with a smaller molecule. We then did it with a bigger molecule because we wanted to see, the reason why we increased the size is we wanted to see if the trend is the same no matter what the size of the molecule is, okay? We could have got that trend just from the top 3, but by doing the second 3, where they're much closer in mass, we can actually see that the trend's exactly the same. All right, so the point is, how does the functional group variable affect the boiling point variable when the mass remains constant? That's our constant, okay, our control. Next one. Which other variable, apart from the conditions for determining boiling point, was kept constant? Now, we've actually just said that. By conditions for boiling points, in other words, what they're saying, besides the initial temperature, besides things like making sure they start as a liquid, all of those sort of things, what was the other thing? We had to keep the mass constant. Okay, over here, molecular mass. Mass plays a very big role in your intermolecular forces. Okay, so I couldn't compare, if we looked at these, I cannot compare A's boiling point to and E's boiling point because E is a much bigger molecule. Okay, and you can see that A is 118, E is 137, so we know it's a bigger molecule. It must have a higher boiling point, but the functional group changed. So that's not a fair test, okay? So we have to keep the mass constant. Then, what conclusion can be drawn from the results in experiment 2? Okay, now look, watch here. What you need to recognize, okay? Your carboxylic acids can have hydrogen bonds. Your alcohols can also have hydrogen bonds. Your aldehyde cannot, okay? Your carboxylic acid can actually have a double hydrogen bond, okay? Because remember, your carboxylic acid looks like this, and this hydrogen can form a hydrogen bond with the double bond oxygen of a different molecule, and this one can form a hydrogen bond with another organic molecule. So it can form 2 hydrogen bonds. That means it has very, very strong intermolecular forces. Okay? Very strong intermolecular forces. So the sort of thing they were wanting, I'm going to just tell you from the official memo because it's going to make it a bit easier, is you can't, it's only worth 2 marks. Okay? So grade 12s, please don't start going into things like, going into a long explanation about surface area and mass and intermolecular force, because that's not what they wanted. They didn't want an analysis. They didn't want an explanation. They wanted the conclusion. And in any experiment, your conclusion must be short and sweet and to the point. The conclusion we can make is that carboxylic acids have a higher boiling point than alcohols, which have a higher boiling point than aldehydes. Simple as that, okay? No explanation needed. Please do not start explaining. It's only worth 2 marks. You're not going to get any marks for those explanations, and if anything, you're not going to get any marks at all, okay? If you need to think it through in your head, that's great, but you can see it from the actual boiling points given to you, okay? And the last question, now, refer to intermolecular forces to explain the trend. Now you can start going. Carboxylic acids have stronger intermolecular forces due to the fact they can have a double hydrogen bond. I'm not going to write it down because I'm going to run out of time, okay? Carboxylic acids have stronger intermolecular forces due to their double hydrogen bond that they can form, which means it takes more energy to break those intermolecular forces, therefore they have a higher boiling point. And I've done it again. Your OH, your alcohols have hydrogen bonds as well, not as many as carboxylic acids, therefore the intermolecular forces are a little weaker, less energy required. Aldehydes have no hydrogen bonds, so in relation to carboxylic acids and alcohols, their bonds are weaker, less energy required to break their bonds, therefore their boiling point decreases. It's actually a lot of work with 3 marks, but they're looking for whether you understand the fact that the stronger the intermolecular forces, the more energy is needed, the higher the boiling point. Okay, and I think, Ty, I'm done.
That time.
We can take a break.
All right, so mindsetters, don't disappear. Make sure you keep on using the page. You know, bond with it. You know, but anyway.
It's just getting worse.
Yes, make sure you stick around. We'll see you after this break. And welcome back, Mindsetters. Hope you had a nice little break. You went and did whatever you had to do. And as I said earlier, now back and you're bonding with us, you know, through the TV and on the page, you know, talking about chemistry, bonding, COVID. And anyway, yes, make sure you don't forget to get onto Curio. And don't forget you can also email us at helpdesk@learnextra.co.za. Just do it so you can just help yourself, you know, because we won't be able to cover all your questions. We'll cover as many as we can. But yes, Mindsetters, keep using the page. But for now, I'm going to hand it over to Phil. Phil, take it away.
Thanks so much, Ty. I see what you did there with the bonding.
Yeah, see, I'm trying. I'm fusing the lesson.
Absolutely. Okay, well, there we go. Let's get into some chemistry. Let's talk about that equilibrium question. Okay, guys, I see on the page, and we've been furiously answering your questions. Keep sending them in, because we're going to try help you. You're going to be helping each other. And we're going to carry on with this equilibrium question. Some of you are asking, how do I calculate Kc? And a lot of you are saying, please, don't ask Kc. It's going to happen, guys. Kc is in your exam. It's got to be in there. So we're going to carry on with this question 9. I'm really loving the feedback that we're getting on the page. So keep doing it. Okay, now let's get into the numbers. Now they tell me that I've got a few numbers here important. Okay, there we go. So 1.5 moles of N2, which is a gas. Now that is the amount of N2 which I'm putting inside my container. Okay, and 2 moles of H2. There we go. So we've got both our reactants. We're putting them inside a closed reaction vessel. Okay, now they do tell us that my reaction vessel has actually got a volume there. So 0.5 decimeters cubed. Okay, it's half a liter if you're looking for something a little bit more easy to understand. Okay, so we've got a closed reaction vessel. Very important to have a closed reaction vessel for equilibrium to take place. And now we're allowing it to reach a temperature of 470 degrees Celsius. That is where equilibrium is taking place. And then it was found, now this is very important, that at equilibrium, now this is very important, that 1 mole of my product, and there we go. Guys, if you are in the fertilizer industry, that product is very important to you. And later on this show, I think we're going to take a look at some chemical systems if we get time. Okay, but let's see what's going on here. So I started off with 1.5 moles of N2, 2 moles of H2. I put them inside a half-liter container, and inside the container, after some time, I found that 1 mole of my product was formed. Guys, the only way to organize your information I'm going to show you today, okay, and it's probably the most frequent question that we get about equilibrium, is how to use the table to find Kc. And I'm going to be showing you a few ways that you can be asked this. Okay, now the way that this question is asked us is say, calculate the equilibrium constant. So they want us to reach Kc. There we go, the equilibrium constant. The C stands for concentration, guys. If you're asking why it's Kc, okay, now this is constant in German, but C for concentration. Now at 473, where did the 3 come from? Okay, so 470 degrees Celsius. And we've got to show all your calculations. Guys, please show me all your calculations. Now, one of the best ways to organize your information is to draw me one of these fantastic tables. Okay, and I've been lucky enough to have this table already written up for me. Okay, but before we get in filling this table, please, guys, I just need to show you something. If you get asked to calculate Kc, this is one of the few places in chemistry where you actually just get marks for writing down an equation. As easy as that, guys. You just got to write down your Kc expression. You don't even need to put numbers inside it. Okay, so guys, you can see that there's 8 marks for this, and the first one is just to come up with the right Kc calculation. Now that's not that difficult, guys. You've got to draw up your table and you'll get a few more marks over there because of some of the assumptions that you have to make. But please, the first of your 8 marks, and even if KC is not your thing, I'm going to show you how to get your KC calculation going before we even get anywhere. Okay, so now before I even take a look at the numbers, let's start to write down what the equilibrium constant, so in other words, a concentration-based equilibrium constant looks like. Okay, so I started out this way. I say Kc equals. Now, a lot of you are starting this by saying Kc equals product over reactant. Don't even do that. You don't get marks for that. They want to know if you can tell which one are the products and which ones are the reactants. Okay, so let's do this together. So here we go. Here are my products. There's NH3. So what I'm going to do is I'm going to put my products inside the square brackets. Now, a lot of you don't actually know what these square brackets mean. These square brackets mean concentration. In chemistry, when you draw square brackets around a chemical, that means how concentrated is it. So NH3. There we go. Now there's something else which needs to go on the set of brackets, and it's the coefficient. It's the number which goes up to the top here. So there we go. Guys, please, that means the concentration of NH3 squared. Now, let me show you something else that you guys are constantly doing wrong when you write up your Kc. Okay, so I see my reactants over there, so N2 and H2. A lot of you, for some reason, want to add them underneath the brackets. No, guys, watch. I'm going to show you how to do this. So, it goes N2, so my concentration of nitrogen, multiplied. Guys, multiplied, not added, multiplied by H2. And something else needs to go on the H2, and this is very, very important, my coefficient. So there we go, my coefficient is going to jump up there and become an exponent of H2. Guys, just being able to do that, being able to read off my chemical equation and make a Kc value, that is going to get you a mark. Even if you don't even know how to do a table, and you should, but if you start out with this, got a mark, no problem. Okay, so let's start to actually take a look. Where am I going to find these values? Now, if you don't know a lot about this section, a lot of people are tempted to go, okay, I've got moles, I've got volume, I can get concentration. Now, the problem is, I've only got the amount of NH3 at equilibrium. Now, this is an equilibrium constant. Now, this is based on values which only come right at the end of my question. I cannot calculate them using the 0.5 decimeter cubed and the 1.5 mole of N2 and the 2 moles of H2. Can't do it because those are initial concentrations. And here, this table is where it starts. Okay, so now a lot of people call this the rice table, and I'm going to show you why. So we start out with the ratio. There we go. The ratio is my first set of information. Then I, so Ri, so I for initial, then C for change, and then E for equilibrium. Now, the reason that there are 2 equilibrium columns here, or at least rows here, the reason that there are 2 equilibrium rows is because one is going to be for moles, which is where we're going to land up, and then the last one is going to be for concentration. Okay, so let's put in my ratio. The ratio comes directly from my chemical equation. So this one's quite easy. So how many N2s? There we go. 1 to 3 to 2. Now, a lot of people say, okay, well, I don't even get any marks for my ratio line because all I'm doing is reading. But guys, please, this sets you up for success because your ratio is right there. You cannot ignore it. Okay, now here's where the magic begins. I start to fill in the initial amounts of N2, H2, and my product of NH3. So my initial quantity of nitrogen was 1.5. Let's just double check that I'm right, that I'm not getting them mixed around. There we go, 1.5 moles of N2, okay? Right, and now H2, I'm going to put in 2.0 moles. And now here's the problem. A lot of people are saying, what about the product? Do I put 1 mole in there? No, guys. These 2 reactants were put inside an empty container. And here's one of those marks that you can actually expect to get. Your examiners think it's very clever when you realize that there was no product at the beginning of the reaction. Now that's very, very important. I put it inside an empty container. Now what else do I know? Something else which I know is that my product at equilibrium added up to 1 mole. So there is 1 mole right at the end. And all of these are measured in moles. I'm working in moles on this table. So I've got 1.5 moles, 2.0 moles, 0 moles. Okay, now a lot of people say, okay, well, how on earth do I start with this table? Now, if anyone's ever done Sudoku or Sudoku, depending on how you say it, what you do is you look for a place where you've got the most information. I see I've got the most information about my product, which is NH3. So let's figure out what's missing, or how did my initial turn into my equilibrium. Okay, and right at the end of this, I actually want to discuss what happens. How do I use X? And some people are saying, how do I do this if I'm not given the change, or I have to work towards that? We'll get there in a moment. Okay, so let's just work through this carefully. Okay, so how do I get from 0 moles to 1 mole? And that's quite easy. I added 1 mole during the change. So there was a positive change in my product of 1 mole. Okay, now, what I'm going to tell you now is that there's 2 of these rows which link up very nicely on my table. The ratio is only allowed to be used with the change. Please, I'm going to repeat that again. You can only use the ratio with the change line, because the change is because of the reaction. You cannot use the chemical ratio with any other of the lines over here. Okay, so let's see, how do I use my ratios to get my change for these 2 reactants? Okay, so I'm going to do this very, very slowly with you guys. Okay, now the way to use ratios, remember that ratios over here. There we go, there's my ratio. I'm just going to actually put in the dots to make sure that people know that this is a ratio. So the first thing which I'm going to do is I'm going to take my 1 mole and I'm going to take it through the ratio. Let's first ratio to get to my hydrogen. Now a lot of people are going to be a little bit confused, so I'm going to do it twice. I'll start with my number of 1. Now I use the number 2. Now the first thing which you do in a ratio, if you've got it placed out like this, I call this a window box because these look like my bars in a window. So I say 1 divided by the same. So 1 divided by 2, and this is just like the triangle that you learned in grade 9 to use your equations. So I go 1, anytime you flip that way, it's divide. So 1 divided by 2. So what I'm going to do is I say 1 divided by 2, and then what I'm going to do to go across to hydrogen over there is multiply. So you divide by the same and then multiply by the one which you want to get to. So I say 1 divided by 2, which gets me a half. Half multiplied by 3 gets me 1.5. So that is 1.5. I'm going to do that again because this is the thing which people ask me for the most. So I say 1, you always divide by the one which you've got over here. Then you multiply by the one which you want. Okay, so I had to say 1 divided by 2 multiplied by 3 gets me 1.5. Let's do it again. So 1 divide by 2. Now I'm going to go across to nitrogen over here. So 1 divided by 2. Now I'm going to move across to nitrogen. So 1 divided by 2 is a half. A half multiplied by 1 is still a half. There we go. Now there's something different about the change when I write it underneath a reactant line. Now I've just got to remember that reactants are used. So any change underneath a reactant is usually a negative number. Because I get rid of reactants, I'm going to use them up as my reaction goes. If you get to this stage, you're almost there, guys. Please make sure that you don't give up. Okay, so now I'm going to find out the equilibrium amounts of each one of these chemicals. So if nitrogen started out with 1.5 moles minus 0.5, what I'm going to land up with here is 1.0 moles. If I start out with 2 moles of hydrogen and I subtract away 1.5 moles over here, what I'm going to land up with is 0.5 moles. Okay, now what I'm going to do in my last of these rows is actually going to use my equilibrium amounts to create concentrations. And remember that concentration is equal to the number of moles divided by the volume. Now they want you to show each one of these calculations. So I'm going to do them underneath here and then just write in the final value in the table. Okay, so for the first one, I'm going to say 1 divided by, now the volume, remember the volume is the volume of your container. So that is 0.5. Okay, so 1 divided by 0.5 gets me 2 moles per decimeter cubed. So I'm writing in my concentrations here. Okay, so now for the next one, what I'm going to say underneath this one, what would be my number of moles divided by my volume? So my number of moles here is 0.5. My volume is 0.5 once again, and I get a concentration here of 1 mole per decimeter cubed. We're doing pretty well. What about the last one? So the very last concentration that we've got to calculate, again, is 1 divided by half gets me 2 moles per decimeter cubed. Okay. Guys, if you get this far and stop, I'm going to be very angry with you, because now all you've got to do is take these numbers and put it into my beautiful Kc calculation. Now I've got concentration of my nitrogen, my hydrogen, and my product over there. So let's do this together. Okay? So now let's just move these out of the way. Let's just make sure that we've got a little bit of space here. Let's get these arrows out of the way. Right, and then let's substitute into my calculation over here. So my NH3 landed up being 2 moles per decimeter cubed. Don't forget to square. It's very easy to forget about the exponents. Okay, what about N2? N2 over here landed up at a final concentration of 2. And H2 landed up at a final concentration, I think it was 1. Let's just double check our values there. So that is 1 mole per decimeter cubed. Right. Now all I've got to do is put this into my calculator. So I've got 2 squared on top, which is 4 over there, and I've got 2 times 1 over there, which lands up as 2. And I've got a Kc that gets me to 2. Guys, there's no units because Kc is a ratio of concentration over concentration, so there is no unit. Guys, please, 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 just some of these tips. Write down your Kc values first, then start to fill in the values which you know on your table. If you are stuck at that stage, don't sit and hold your head because you're wasting time. There's other questions which you can answer very, very quickly. Okay, so write down your Kc expression, write in zero product, move on. Now, I told you I was going to discuss when to use X, when to use an unknown on the change line. Now, in those cases, they're actually going to give you Kc and ask you to work backwards. Okay, so slightly more complex ones. If we get a little bit of time at some stage, we'll be able to do those. But guys, the only time that you're going to do those, and those are very nasty, is when they give you Kc and ask you to work backwards. If you are put in that case, the hint is to use the change line, is to use X on the change line. Now, I'm not going to spend too much time on here, but all that I'm going to say is follow your steps on this table, and it's going to get you there. Practice makes perfect, guys. Okay, now we're going to analyze our Kc. Now, this is very, very important. How temperature, how pressure, how concentration all affects your Kc. Now, let me start off by saying this. The only thing which affects Kc in an isolated system, and that's quite important to know, that if it's a closed system, well, not an isolated system, sorry, that's a correction. If it's not a closed system, right, all that can happen is things can go in and things can come out. That is not a system which is closed. In a closed system, temperature is the only thing which can affect the Kc. Pressure cannot. Okay, but now we are dealing with temperature, and somebody asked on the Facebook page here. So it says the temperature is now increased. There it is, to 800 degrees Celsius. There's a stress involved. Le Chatelier is going to be involved here. So it says, how will the value of Kc be affected if the temperature is increased? Here we go. Right, to 800 degrees Celsius. Right, only increases, decreases, or remains the same. Okay, now grade 12s, if you're in the situation where you don't actually know how to apply Kc, best option, make a 1 of 3 guess here, but I'm going to show you how to make it an educated guess. Okay, right, now the first thing which we need to know if temperature is involved is the reaction exo or endothermic. This reaction, the forward reaction, was exothermic. That means that delta H, now this is not part of your answer or anything, they just want one term. So delta H over here was less than 0. That means that this is an exothermic reaction. Now, an increase in temperature is not going to help an exothermic reaction. It's going to help an endothermic reaction. So we're going to get reverse reaction favored. So I'm just putting some notes here. You don't have to do this when you're answering this question. Look at the mark allocation, 1 mark. So reverse favored. And we're going to have to do this in the next question anyway. So the reverse is favored because of Le Chatelier. Okay, so I've got a negative delta H. I've got my reverse favored, which is going to drop the products, which means that my Kc is going to decrease. Guys, the Kc is going to decrease in this case because I'm favoring the reverse reaction. Okay, now here's the money question. It says, explain your answer to question 9.6.1. Okay, now what I can tell you, first of all, is that you've got to identify that, first of all, my forward reaction is exothermic. Okay, so exothermic. It's quite important that you identify the forward reaction is exothermic. You may not get a mark for that, though. They've probably given you this information. The forward reaction is exothermic. But what you can say is that an increase in temperature favors the reverse reaction. Now, this you will get a mark for. So an increase, and this is very important. So increase in temperature, and because an endothermic reaction needs temperature to function, so an increase in temp favors an endothermic reaction, which is the reverse. So it favors the reverse because it's endothermic. And I hope you guys are taking notes here, because this is always going to be the case. If I increase the temperature, I'm going to favor the endothermic reaction. So it's an increase favors the reverse, which is endothermic. Okay, now that you will get a mark for. Now, you've got to mention that you know what Kc actually is. Kc is a measure of products over reactants. So if I'm favoring the reverse, what you'll find is that my concentration of my products will go down, so my products concentration will go down. And what else will happen is that my reactants concentration will go up, therefore. Now notice how I only talked about the Kc right at the end, because Tracy was telling me in the back studio, she was actually telling me, you guys are not explaining yourself properly. Now what you're saying is, well, I know the Kc decreases, and that's why it decreases. You haven't actually explained anything. You've started with your answer and assumed it to be true. Now, when you're explaining something, you've got to put into place the steps that get you to your conclusion. I've got to say, okay, well, increase in temperature. What happens as a result of increase in temperature? Well, it favors the reverse reaction, which is endothermic. Okay, then what happens? That means that my products are going to go down, my reactants are going to go up. And that is why. I can only end off with the thing that I'm trying to prove. Guys, it's just like maths. If you're trying to prove something, you cannot assume that it's true until you put in the reasons first. Okay, and this is probably one of the most commonly asked questions in Kc equilibrium. Guys, I hope you enjoyed that. I think we're going to give them a little bit of a break.
Yes, because that was jam-packed.
Absolutely.
All right, so Mindsetters, make sure you don't disappear. Stick around. Keep on using the page. Keep chatting to us. I'm loving what you guys are doing on the page. It is awesome, awesome. So make sure you keep on using the page. But for now, we're going to see you after this break. And welcome back, Mindsetters. Hope you had a nice little break there. And you're active on the page. I just wanted to say thumbs up, guys. Thank you so much. It's so important that you do that. And don't forget to sign up for Curio. And if you have any other questions, make sure, if you can't get it on the page because it's just too long, make sure you email helpdesk@learnextra.co.za. So we're going to continue the rest of the show. Tracy, take it away. Hi, Magic.
Thank you, Ty.
No
Okay,
problem.
guys, you guys are seeing lots of questions. We realize a lot of the same sort of thing. We obviously get into as many as we can. We're going to look at fertilizers now because we know this is going to come up. So we are taking it from the 2008 paper, and it's just from question 12.3. First part was on eutrophication. We're not going to worry about it. So the flow diagram below represents the conversion of ammonia into nitrates, okay? I'm not even going to look at the bottom part of the questions yet. Let's go through what the flow diagram tells me. Then we're going to look at the questions because it'll probably guide me as we go along. Okay, so we've got, first of all, we know it's going to make a fertilizer. So we know fertilizer P is going to be ammonium something. Okay, now we're going to figure out what that something is going to be. We're taking ammonia, which is becoming nitrogen oxide, which means what process X is the catalytic oxidation. Catalytic. See, I am learning to spell today as we go along.
That's always very handy.
It is. It's one of those things. So, and not that that's even vaguely legible, but let's pretend, which means I'm adding O2 to it. Then from the NO, I'm making some other gas, which pretty much the only other gas I'm going to be able to make is NO2. And then I make a liquid. Now, the liquid we're going to make from NO2 has to be nitric acid. So this three-step process from ammonia to HNO3, has to be the Oswald process. Okay, remember we make ammonia through the Haber process, okay, which you've done ad nauseum since grade 10. Hopefully you know that one. We make nitric acid through the Oswald process, which then means if I'm going to add ammonia to nitric acid, it means that I make ammonium nitrate. I'm making a very strong nitrogen-based fertilizer. Okay, first question. What is the name of process X? Oh, look at that. Answered it before we even looked at it, the catalytic oxidation of ammonia. You've answered it. Now you don't have to think about it. Now you don't have to go, not sure. It's there. Okay, next one. Write down the balanced equation. Now the fun part starts. So, we know we've got ammonia plus oxygen, which is going to give me NO, and then you need to realize that we're going to get water. Okay? Now, get to this stage, you've got 2 out of your 3 marks. If your balancing of chemical equations isn't so great, and this isn't, you're like, it's a bit shaky, please don't spend the next 3 hours, figuratively speaking, trying to balance it. Okay? Let it go, move on. It's unimportant, but let's balance it anyway because it's an important skill. So, let's go 1 nitrogen, that's cool. 3 hydrogens, 2 hydrogens, that's a problem. 2 oxygens, okay, hydrogen is going to be our problem, which means let's start by, let's make the hydrogens balance. So if I put a 2 over here, gives me 6 hydrogens. Let's put a 3 over there, gives me 6 hydrogens. But now we've got a problem because now I'm going to need to put a 2 in front of that, NO, to balance the nitrogens. And now the oxygens have just fallen off the map because now we've got 2 oxygens plus another 3, that's 5. That's a problem because I can't get that to 5 because it's a even number. So let's do, we don't want to multiply this hydrogen by 3 because if I multiply it by 3 then it gives me 9. I can't get 9 over here, it's an even number, so let's multiply this by 2. So let's change this 2 out and multiply by 4 rather. Okay, so I'm going to put a 4 over here. Now what that does is it's going to change this number and it's going to change that number. Okay, let's not get rid of our arrow. And if that gives me 4 nitrogens, so let's make that 4 nitrogens. 4 times 3 is 12, which then means I'm going to have to multiply this hydrogen by 6. Gives me 12. And now let's look at the oxygens. 4 oxygens plus 6 oxygens is 10. That means I'm going to have to multiply that one by 5. Okay, now I can do this quite quickly because I've been doing this for a long time. If you can't do the balancing, leave it. The important thing is that you get the products and the reactants. Then, write down the formula for gas Y. Look at that. Done. We don't even have to think about it. You see why I'm telling you? Work through the flow diagram. These are brilliant ways of testing lots and lots and lots of stuff. Okay, so we're going to write down the formula because that's what they wanted. So it's NO2. And now they say to you, write down the balanced equation for the preparation of fertilizer P. Okay, we realized we were finding nitric acid. So that means we're taking NH3 plus HNO3. And these together are going to give me ammonium nitrate. Okay, NH4, NO3, okay? Now we look at this and we go, let's see, 1 nitrogen, 2 nitrogens, 1, 2 nitrogens, we're happy. 4 hydrogens, 4 hydrogens, 3 oxygens, 3 oxygens, balanced, done. Okay, nice and simple. We could have asked you, and I think that's the last question, we didn't do the next one. We could have asked you all sorts, bless you. Ty's just busy sneezing in the process, okay? We could have asked you all sorts of things along here, okay? What is the process called? We could have asked you how do we get from NO2 to HNO3. They could have asked you to name the nitrate, okay, to name fertilizer P, we could have asked you we did actually ask you without actually making it look too official, what the O2 was, okay? So guys, the point is, you are going to get at least one of the chemical systems, or more, okay? And in fact, in the KwaZulu-Natal prelim paper, it was such a nice flow diagram because they asked the Oswald process as well as the contact process in it, in one thing, because what they wanted to get to at the end was ammonium sulfate. So that's incredible. That's such a nice process to ask. It's a nice way round it. Or was the Haber process, sorry, and the contact process. Guys, we can ask you lots around it. They're also going to ask you around this. Remember, it's an inorganic fertilizer. What happens when we over-fertilize or we use too much? We get eutrophication. Okay, by now, if you do not know that word with an E, go and study it. You're probably going to get it. Remember, eutrophication is when there's excess nitrates in our groundwater, in our lakes, which then causes algae bloom, which then causes fish to die. It's bad, bad, bad. But why do we need fertilizers? Because without fertilizers, our crop yields are too low. And remember, we have an expanding world population. We've got to feed us somehow. Okay, and I'm pretty sure most of you are grateful you can get to the shops and get food. I am. I wouldn't want to have to grow my own crops because I do not have a green finger, no pun intended, and all my plants die. So I'm very grateful somebody else grows them for me because it just wouldn't work for me. Okay, guys, you're going to get these. Do not just look at the flow diagram, okay, and then start answering the question. Work through them. Okay, I really, really do think you're going to get a flow diagram somewhere along the way. Okay. The other processes you can get are your chloralkali industry. We haven't spent much time on it. That's going to get asked within your electrochemical cells and your electrolytic cells and the use of electricity and the conversion of electrical energy to chemical energy and all those wonderful things along the way, which you really, really hate. We're getting lots of questions on that. Just keep watching. I'm pretty sure Phil's going to do one next. Okay. And I think we've done everything we need from here. Remember important words like catalytic oxidation. Why would we need a catalyst? Because otherwise it happens too slow. There's a time factor. This is industry. The faster we can get our products at a reasonable rate, at a reasonable cost, the better it is. It's the same reason in all your industries. Make sure you know the conditions for the Haber process. Make sure you know the conditions in the contact process when we make SO2 go into O2, which makes SO3, okay? And it's that whole balance between economics and speed, okay, and safety. Just because we need a high pressure to get something done doesn't mean it's safe. So we have to have that toss-up in the economic balance, so we make compromises. It's a good way to ask equilibrium. You were just doing a KC calculation. Remember, you can be asked the Chatelier's principle in that. Economic factors come into play. Why would we have the conditions we have? Because we want the highest yield at the best rate, okay? We don't want a high yield, but it takes forever, but we also don't want a low yield that takes really quickly. We've got to make a compromise. Okay, so grade 12s. I actually think, and I know I've done this quite quickly, but I know Phil's still got a lot that he wants to have done. He's got a really nice question coming up, so that's going to be me for now. But guys, keep posting. We get into as many of your questions as we possibly can, okay? So keep posting. Read other people's comments. There's been some really, really good ones. There's a couple who are really good at answering the questions as well for each other. So keep on the page, okay?
Yes, so while Tracy tries to hijack my job,
Sorry.
anyway, mindset is
Didn't I do
keep
that on
using-
Friday as well?
Yes, you did. And I was like,
Sorry.
seriously? But anyway, mindset is make sure you keep using the page, keep talking to us, and don't forget to sign up on Curio and email us, helpdesk@learnextra.co.za. And we'll be right back after this break. And welcome back, Mindsetters. Hope you had a nice little break there. Now you're back, you're ready. You've been working on the page, which is just awesome. I just want to say thumbs up again. You guys have been great. Keep on posting, keep on letting us know what you're thinking. If you're lost and if you need help, let us know. Post on the page or email us. In fact, not or, and email us. helpdesk@learnextra.co.za. And yes, we have a session to do, so we have a couple of minutes left. So Phil's going to fill the rest of that up. Get it? So
I saw
handing
what you
that
did
over.
that time. Okay, well, guys, you're going to be, well, you have been asking for it, and we've been asking some questions of you, and some of you said, okay, well, electrochem. Okay, now, electrochem, we've been doing it, but you guys can't get enough, so we're going to do our last little section on electrochemistry. Okay, so let's get into it. Time is short, so it says learners conduct an investigation to determine which combinations of two half cells will produce the largest EMF. So we are looking for voltage, ladies and gents. EMF is electromotive force at standard conditions. Okay, so we'll discuss that in a minute. So it says 3 half cells represented as A, B, and C in the table below are available. So half cell A has got magnesium and magnesium ions. Half cell B has got lead and lead 2+, and aluminium has got aluminium and aluminium 3+. Okay, so now we've got to figure out which combination is going to get us the most voltage. Okay, now it says that the learner set up galvanic cells using different combinations of the above half cells. So we're going to have some A with B, we're going to have A with C, and then we're going to have A plus some C over there, and we're going to see which one is going to give us the most voltage. Okay, so it says write down the standard conditions. Okay, so I started this already, so it says write down the standard conditions under which these cells operate. Okay, now these standard conditions over here, and we didn't have time to finish them off. The most important one, by far, is that we're operating at 1 mole per decimeter cubed. There's another very, very important one, which I just want to discuss with you quickly, guys, because both of these actually affect the EMF of a cell. And that is the temperature. Now, this is not the same standard temperature as for your gases, which is 0 degrees Celsius. It is 25 degrees Celsius, because at 0 degrees, all the solutions would be frozen. So 25 degrees Celsius or 298 Kelvin. You don't have to say degrees Kelvin, it is just 298 Kelvin. Now, if there were gases involved, there's another standard condition which we could actually add up to the end there, is that we are operating at 1 atmosphere. And 1 atmosphere is equal to 101.3 kilopascals. Okay, that is the air pressure down at the sea. Up in Johannesburg, it's just underneath 100 kilopascals. Okay, so we're breathing in slightly less air. Okay, so standard conditions, very important. Right, now see that there are only 2 marks here. So those first 2, concentration, temperature, just a reminder that those 2 can actually affect the EMF of my cell. So all of them on the table have got to be compared using that. Now, here we go. We're going to get into the investigation. So write down the dependent, okay, and the independent variable we can identify as well. Now, I'm actually going to identify the independent variable first. Okay. So now, when we're starting to take a look at this question, they asked us to investigate the effect on 2 variables. One of them was EMF, and one of them was the half cell. Now, which one did I have control over? Okay, guys, I had control over which half cell? Now, that means that the one which I have control over becomes the independent. Right, so independent starts out with the letter I. So there we go. Independence, there we go, is the half cell. Okay, now dependent, the dependent half cell. Right? Now what depends on the half cell? So what is dependent on it? Let's just make sure we move that correctly. The EMF is dependent on the half cell. So which half cell I choose is going to result in a different EMF. Okay, now let's jump into some more of those questions about this. Okay, now it says use a table of standard reduction potential. Some of you call this a redox table to determine which one of the 3 half cells, A, B, or C, contains the, now, strongest reducing agent. Okay, there we go. So the strongest reducing agent. Okay, Now, what we've got to do is we've got to study this half table very, very carefully. Okay, now the one thing which this table is missing slightly is it actually gives us some arrows. Now, let's actually make some really nice fat arrows so that you guys can see what's going on. Okay, so that's pretty fat. Now, what we're going to do is we are going to analyze this thing. Your table has actually got these arrows on. Now, what it does is the one on the right points upwards, and the one on the left points downwards. Okay? Now, what these arrows actually do is they point out the strongest reagents. Okay, so over here, these guys are reducing agents. Now, my reducing agents are all found on the right-hand side. Okay, so my reducing agents over there. Now, what you can tell about all the reducing agents is that all of them undergo oxidation. Now, you can find that lithium, if I chose lithium, lithium goes across, and that means oxidation because it's losing electrons. Okay, but before we do that, let's find the ones which we're actually talking about. So there we go, I'm rubbing out my reducing, I'm getting so excited about this. Let's circle all of my metals. Now, we had lead, we had mercury, sorry, we didn't have mercury, we had magnesium. See how excited I'm getting. Okay, so magnesium, right, we got some lead over there. There we go, PB. There we go. So we got some PB, and we've got some aluminium. Aluminium, I think I'm going to find a little bit higher on here because aluminium is quite reactive. Okay. Now I'm asked to choose. Now I've circled 3 reducing agents. I know that they are reducing agents because Mg going across the other side is oxidation. So reducing agents do undergo oxidation. Now, how can I tell which one is the best? And here is the clue. Guys, the arrow is actually there to help you. It's pointing at the best one. It couldn't get any simpler than this. The best one is going to be the one at the top. I can see that an arrow is pointing that way. So what I can actually find is that magnesium over here, this guy, is the best reducing agent for the job. Okay? It is the most likely to undergo oxidation and not reduction. Okay, now these numbers on the side can actually give us a clue, but that's actually a much more complicated way of understanding it. The arrow tells me that the one furthest up at the top is going to be the best one. Now, you might say, okay, well, why didn't he consider all of these? Mg2+, aluminium 3+, and what about that lead? Lead 2+. Why don't I consider those 3? Well, those 3 are oxidizing agents. They undergo reduction. So remember that your agent always undergoes the opposite because an agent is trying to get something to happen. Magnesium 2+ is trying to get oxidation to happen, so therefore it is the oxidizing agent. Aluminium 3+, Pb2+, those are all oxidizing agents. Okay, so what was the question talking about? It said write down the strongest reducing agent, and let's do exactly that. So there we go. The strongest reducing agent over there is Mg. There we go. Nice and easy, 1 mark. Don't write any explanation. Now the strongest oxidizing agent. Well, if we were studying our table very carefully over there, our table over there had our strongest reducing agent. Let's bring up our arrow. My arrow is pointing downwards, ladies and gents. Let's take a look at the one which is furthest down at the bottom. This is not so hard. All I've got to do is select the best one for the job, and that is Pb2+. There it is. There is my strongest oxidizing agents. So I found all my oxidizing agents on the left, all my reducing agents on the right, and it's really easy if you understand it that way. So there's my oxidizing agent. It's the best one. It's the furthest down. Let's write it down. It's Pb2+, not Pb. Pb2+ is the correct format of that. So let's write that in. So Pb2+ is my best oxidizing agent. Okay. Now it says, without any calculation, write down the combination of 2 half cells which would produce the highest EMF. Well, I can tell you now, when you've got the best reducing agent with the best oxidizing agent, that is going to make the biggest EMF. And I'm going to show you how to predict that. Now, if you start to draw lines between these guys, and what I mean between these guys, so from Pb to Mg, if I start to do from Al to Mg, or Mg to Mg, what you're going to find is 3 lines there. Now, you could do it the other way, but what you can actually see is the steepest slope. So the most angled slope is the most spontaneous, the most exothermic, the one which gives you the most energy. So that is the steepest one. So what I'm finding is that lead and magnesium together would give the steepest gradient. In other words, we're trying to find voltages which are the furthest away from each other. The bigger the difference between these two numbers, the higher the EMF. Guys, that is how to figure out. Now, they don't want any calculation. They just want to know which one with which one. So that is lead and that is Mg. Now, if I remember correctly, let's just go back to our combination of cells over there. Let's find out the best ones over here was going to be Mg with Pb. So that is combination A with B. And that is going to give us the maximum EMF. Now, the maximum EMF will be A linked up with B. Now, if you really wanted to, you could go and calculate the EMF, and I'm not sure if we've got time, but I'm going to do it quickly. So we're going to do a quick E0 cell. So now an E0 cell calculation is my E of my cathode, which is where reduction takes place, minus E of my anode, and let's actually do it together because we've got a calculator and about a minute left. So let's actually substitute inside my brackets. Let's find out what those values are. So on my redox table there, so negative 0.13. Now, is this anode or is this cathode? Well, since this is reduction, this is my cathode. So there is my cathode reaction. So negative 0.13. So let's write that in over there. So negative 0.13 goes into my cathode reaction. And my oxidation reaction, 2.37. Just remember that that is also negative. So 2.37, let's put it in there. So negative 2.37. I hope you can see why I'm using negative and brackets together, because that's actually going to help me. So that goes minus 0.13 plus, and that's why I use brackets. So 2.37. So what I'm actually going to find is that that is going to make 2 points. I think that is 2.2. Let's just make sure that we're doing this correctly. So 2.24. No, that is absolutely correct. There we go. So 2.24 volts would be the voltage which I can expect out of this. Not asked, but we did it anyway. Okay, guys, I think that's it from me after that turbocharged calculation.
That jam-packed session with all of that. So mindsetters, I hope you guys are doing the right thing, remembering your 3 Ps, pens, pads, and phones, so you make sure that you talk to us and let us know that what you guys are thinking. But mindsetters, I cannot stress enough, keep using the page, keep on posting, and again, if you need help, feel free to email our help desk. But for now, this is where me and Phil say thank you for joining us, and mindsetters, I just want to wish you all the best of luck for your exams, and don't forget to get onto our events page and use our events page to find out what subjects are coming up for exam school. And yes, mindsetters, keep on practicing, keep on working. But this is where I say thank you and see you next time. Cheers.